This video will introduce carbohydrates and review some organic oxidation as well. So carbohydrates include the sugars and starches that we consume every day in our diet. So we're going to focus first on glucose and other monosaccharides to start off with. But the big idea here is that carbohydrates are the primary source of energy that we have for the human body. And another big idea here is that our food gets oxidized and that provides us with energy. So that's why we eat food for energy. So we've got an apple here just to sort of remind us that we have these sources of sugars in our everyday life. So fruits like apples contain glucose. Apples also contain fructose, and they contain sucrose, so the disaccharide as well. So anyway, fruits are a common source of monosaccharides like glucose. So we've got an apple here, and then we've got our first monosaccharide, D-glucose, to look at. Now, our monosaccharides are often written with the carbon chain going down vertically. So we see a main carbon chain here, 1, 2, 3, 4, 5, 6 carbons written top to bottom. Now on that top carbon, we see that it's bonded to a hydrogen on the left and it's double bonded to an oxygen on the right. So if this carbon has a C double bond to an O and an H, that is an aldehyde. So we see that there's an aldehyde here for our functional group. So that's our first carbon. On our second carbon, there's an OH on the right and an H on the left. And our third carbon has an OH on the left and an H on the right. And our fourth and fifth carbons have OHs on the right side and H's on the left side. And then on that bottom carbon, it's CH2 and an OH. So these carbons have different stereochemistry around them. In other words, they have, 4 unique things around each carbon and unique stereochemistry around most of these carbons. In other words, some of these carbons are chiral, and that's going to be important where they have 4 or more different groups around them. Now it says plus 2Cu2 plus, blue. So this is really representing having our Benedict's reagent. And then it says with OH minus, so with hydroxide, so in the presence of base, reacts to form gluconic acid. Now, that is still our 6 carbons all in a row going down, and the whole chain is the same. So no change in any of the OHs, but we do notice that our first carbon has a C double bond O, and now just instead of having the H for aldehyde, we have an OH. So we have a C double bonded to an O with an OH on it, or we have our carboxylic acid functional group. So we'll label our carboxylic acid functional group. And then the other product is, it says Cu2O, or copper oxide that's brick red. So in other words, we have copper 1 oxide that's brick red. And so this copper has been reduced. Our Benedict's agent gets reduced. It actually goes from copper 2 plus to copper plus 1. It was still a 2 minus. It goes to copper plus 1. That's how we know that it goes from 2 plus to 1 plus. It's been reduced. And our glucose gets oxidized to a carboxylic acid. So glucose gets oxidized. Sorry, that got a little squashed in writing it. Glucose gets oxidized while that Benedict's agent reagent gets reduced. So while something's being oxidized, something else has to be being reduced at the same time. It's like this little partnership that has to go on. So let's just review organic redox just a little bit before we get going in this unit. Let's do a mini review of organic redox. So as a reminder, oxidation means that your number of C to O bonds increases and your number of C to H bonds actually decreases. And reduction is the opposite. Your number of CO bonds decreases while simultaneously your number of CH bonds increases. So where have we seen some of this? Well, we've seen reactions of primary alcohols, for example. Okay, so with a primary alcohol, you have an alcohol, you have a carbon that has an OH, and that carbon is attached to one other carbon and two other hydrogens. So it's primary because it's attached to one other carbon. And we used, strong oxidizing agents. Strong OA for oxidizing agents, right? We usually used a dichromate, where we saw the use of a dichromate in our lab. So we were using strong oxidizing agents. In the body, this is going to be enzymes. We're not going to be using dichromates. We're going to see enzymes being used to oxidize or create one more bond to oxygen. So our OH is going to be a C double bond O converted to an aldehyde. And our strong oxidizing agent will take that aldehyde all the way to a carboxylic acid. So it'll continue the oxidation. So a strong oxidizing agent would just continue this. We could also, throw in to conduct this last step, a weak oxidizing agent, right? This could be our blue Benedict's, for example. Our Benedict's reagent could be that weak oxidizing agent to oxidize to a carboxylic acid. Okay, and then just to wrap up our review, we also saw what happened to secondary alcohols. We saw that if you had a carbon bonded to an OH and it was bonded to two other carbons and one hydrogen, that if you took your strong OA oxidizing agent, again, let's say it's a dichromate, like Na2Cr2O4, you're going to oxidize that secondary alcohol to a ketone. Okay, and so far we have said that if we tried to oxidize that ketone, we would have no reaction. No reaction with the dichromate, for example, as a strong oxidizing agent. So let's kind of hold that thought, and we just might see changes to some of those reactions in terms of enzyme possibilities, right? But this is what we've seen so far for chemical organic redox using strong oxidizing agents, so oxidizing primary alcohols all the way to carboxylic acids, oxidizing secondary alcohols to ketones. Actually, let's label this ketones. And then we didn't see any further oxidation so far of those ketones. And by the way, we were able to do just the aldehyde to carboxylic acid with our weak oxidizing agents as well. So that concludes our little introduction / review for now.